writing the AI to create these plans on the fly. That's the problem we are going to look at. Here's another example from a virtual world domain. This is a game called Tag, which is the children's game of hide and seek. Everyone hides and you're it. You have to go find the other guy, and then they get tagged and they have to find you. This was built in Unreal Tournament. And so these are examples of AIs that power the characters in the games. There's another kind of AI that you can think of as the director, or it's often called the drama manager in the entertainment intelligence field. This is an AI that's not part of the game. It's actually focused on the author's goals in building the game. The goal has a point. The point may be to entertain you or to educate you or something else. And so this AI is focused on the author's rhetorical goals. It watches over the interaction of the game and the human players, and tries to adjust the game to make it better experience for the humans from the perspective of these goals. So for example, this is a project we did with Anchorhead, which is a very old and well-known text game, text-based adventure game. We put a graphic interface on it because nowadays it seems like no one wants to play these games if you have to type text to it. And the idea is that the game, so over here on the left is kind of the game engine. It watches the game state. Over here on the right is the drama manager. So the game engine is watching the human play the game and changing the game to make it more interesting. So for example, in this one example, the user has gone in and out of this shop a few times. You can see from their wanderings that maybe he's a bit of a novice in this game. And the shopkeeper or another character comes in and gives the player a hint. And we're not going to change the experience, spoil the experience for the human, so we do it in the context of the game. The shopkeeper might say, or the other character might say, that silver locket looks curious. And that draws your attention to it, maybe then you go pick it up. Another example, if you're trying to go into a cathedral and you're an expert player, you might find the door locked, because if you go in and find whatever's inside, the game becomes too easy for you. So these types of AIs are also of interest from a kind of a gaming perspective, experience perspective. So why is it hard to build these AIs? Turns out that these games, and if you've ever played with these games or tried to build AIs for them, you know this already, these games are extremely hard from an AI perspective. The stage space is huge. You think of World of Warcraft, there are thousands of possible states and actions. The states are non-determined, the game is non-deterministic. The same action performed may lead to different results. It's also real time, because the opponents are all playing against you constantly. The game doesn't wait for you, unlike chess. You have to model a very broad range of, I can try this, or the big stick. Very broad range of human-like behaviors, goals, strategies, plans, teaming behaviors, emotions, personalities, lots of things that are important to the games depending on the game. Not every game needs all of these, but to do AI in general, you do need a range of these. And lots of people have argued that classical approaches in AI don't work in these types of situations. They don't scale and they don't capture the rich nature of these games. In fact, games are what we call AI complete. And this is interesting. This is a quote from The Economist. It's not technical people talking. They're saying games require players to construct hypotheses, solve problems, develop strategies, juggle tasks, make decisions, learn. And The Economist actually is pointing out that human players who are good at games need to do all these things. They're making the argument that if you're trying to hire people, you should hire people who play games, because they're really good. They make good employees because they have all these skills. From my perspective, if humans have to do all this stuff, then so must game AI. That's the AI we have to build. So game AI is hard from both a theoretical perspective and a practical perspective. On the theory side, we have to model all these things that I mentioned in these very large-scale worlds. On the practical or engineering side, if you look at Facade, which is one of the best-known interactive virtual dramas out there, it has over 200,000 lines of code in a specialized programming language called ABLE, which stands for a behavior language, for 2 non-player characters in the game. It's just 2 characters in the game and you as the player. Hans Christian Andersen, the game I showed you earlier, the AI part of it, for one character, for just Hans, took as much human effort to program as everything else about the game put together, including the game mechanics, the gestures, the physics engine, the speech, everything. So the AI is a huge engineering effort. So the problem is that from both theory and behavior and engineering perspective, how do we enable, even experts find it hard to build game AIs, how do we enable end users to do so? Okay, so that's a challenge problem. I don't pretend to have solved it. Would like to encourage folks to start working on this. Again, if games aren't your thing, look at other types of problems. Because eventually, for AI to really take over the world, we have to get it out of the domain of a few experts and into the hands of everybody. So my answer to this challenge problem is case-based reasoning. Case-based reasoning, as you all probably know, but for just a very quick refresher here, is this way of reasoning about problems by remembering old problems and reapplying solutions. So if you have up here a new problem coming in, you look in a library of past problems to find past cases that are similar, you adapt them to the new situation, and that produces solutions which, if they work, or sometimes if they don't work, can be learned as new cases, new lessons for next time. So that's how CBR works. The research issues in using CBR for games are quite interesting. CBR typically has not been applied to real-time problems. They have not been applied to these situations where you need a planner and executor to work in parallel on the fly. Here we have cases that have to be retrieved, adapted, combined, and repaired on the fly. The effects are unknown, so unlike in typical planning systems, you can't write operators with post-conditions. You can write preconditions, but post-conditions are known because these domains are non-deterministic. And so what we're going to do is create a CBR system that can create these partial plans on a strategic or proactive basis and then expand the plans reactively. So for example, in World of Warcraft, you have this peasant that's going to harvest gold. We have to train the peasant, we have to build barracks for the peasant. We're going to train a knight and then attack the tower. We don't yet know how to attack the tower. There's no point trying to plan it right now. That may be 5 minutes hence into the game. So we're just going to have this partial expansion and then fill in the details on the fly. So it's kind of a hybrid planning and reaction approach. And then of course there's a big problem of where do all the cases come from. Okay, so let's now tie it back to this theme of how do we allow a user to create an AI like that. And it'll tie back to the research question that I just mentioned. So we have 3 types of approaches. The first one is to allow people, like the kids playing Scratch, to create these behaviors using a very simple graphical visual programming language. Scratch, if you haven't seen it, is a lot like Lego Mindstorms in this programming style. This came out of the same group. So it's a visual programming technique. There's no code to be written, but of course it is writing code on the back end. Having done that, the system will fix any problems or bugs in your code automatically through meta reasoning, through analysis of what it's doing right, what it's doing wrong. And then we are also going to give a way to the user to create behaviors by demonstration. And I'll show you all of these techniques in more detail, but you can think of this as a way to author these behaviors, debug or adapt these behaviors, and then create the behaviors through demonstration. So let's start with authoring. So the vision is this: we want you to be able to, you're creating behaviors for Hans Christian Andersen or some other domain. We want you to be able to log into the virtual world, choose a scene that you want to play, choose the characters, behaviors you're authoring, author the behaviors, and I'll show you what that looks like. Play out your scene, and if it works, share it in a behavior library for other people to use. Much like you can go into YouTube or Flickr and remix and mash up all of the media, you can do the same with behaviors as well. So the way the behavior editor works is there's kind of a timeline that this little head comes up. We modeled this after GarageBand or iMovie and these other kinds of things because kids are good at doing stuff like that. We tried these more complicated hierarchical flowchart type editors. It works great for folks like us. A lot of average people don't think in terms of hierarchies and flowcharts. They find timelines very natural. And there's some nice work in Manish's, my student Manish Mehta's PhD thesis showing how this kind of approach is a lot more understandable to an average user than a hierarchical type of approach. And so you just kind of click and drag. So we're going to click and drag a behavior for a user to, an avatar to greet you when you go into the game. So we've created a greet code, and we're going to explain how the goal should be met. In this case, the avatar is going to wave, going to smile, and it's going to say something. We'll just type that in natural language, hi there, and we can kind of drag the goal and say these 3 actions together accomplish the goal. The other person may now greet you back, and then you can also click and add tags and so forth. We're going to make this very simple. We're going to make it all tag-based so other people can find it. And if you need a greeting behavior, you can search for a friendly greeting. And maybe the tags you put in, like friendly and quiet, etc., will find this behavior, and you can go bring it up and change it if you want, and save it back and share it. It's that easy. And so we built a system. It's called Second Mind. It's connected to Second Life. Second Mind, the word is kind of a play on the words. In Second Life, you're creating an alternative life for yourself. In Second Mind, you're creating this extra mind, or a second mind for your avatar. And so now when you go into Second Life, and you go play around for a bit, and then you go to sleep, your avatar doesn't turn into a zombie. It can keep playing in your style because it knows what you want it to do. We have some nice results coming out that Manish is just finishing up the experiments. Should be available literally within a month or 2. So that's the editing part. You've now authored these behaviors. What happens if you made a mistake? Now, it might be, maybe you've authored them using old-fashioned programming or scripts. We all make mistakes because of programming. So you created this behavior, however it might be. How do you know that the character isn't doing the right thing? In the game of tag, for example, part of the experience here was the personalities of these players. So Jack over here is kind of easily frustrated, doesn't have a lot of patience. If he gets tagged too often, he'll walk off. Jill over there is quite aggressive. She'll taunt you when she catches you, and so forth. So you've created the behaviors. How do you then now detect that maybe Jack isn't behaving quite the way you wanted him to do so? So our answer to that is meta reasoning or reflection. Again, something that several people here have talked about as well. So here on the left is your NPC, non-player character. It's got a set of goals and a set of behaviors, and is acting in some game environment like tag or like any other game that you might have. We build a meta reasoner that takes a trace of the thought process of the NPC, so not just the actions, but just the reasoning process itself, and tries to match patterns of failures, things that might be wrong with this reasoning process, and then brings in modification operators or tweaks or whatever you want to call them to go change the behavior library. And this can happen on the fly, so the character is modifying itself as it plays. Our first pass at doing this, and this was presented at ICHCAI a couple of years ago, was kind of the standard approach that if you've been following my work, or Avnar's, a lot of us in the community have been doing this. We build these explanation patterns, or in this case, a finite state machine, or some other kind of pattern language that describes the kinds of things that may go wrong. Look for a failure that has, in this case, there's a critical behavior that doesn't start within some minimum time. You know something's wrong with the trigger conditions. So you can build these pattern libraries. This idea actually goes all the way back to Sussman's work, way back in the old days of AI, and Chris Hammond and others have done similar things. So the problem with this approach is, this actually worked quite well for us. The problem is we now have to start crafting these patterns. We have to author all of the ways in which behaviors can fail in different types of situations. That itself becomes a knowledge engineering effort. In our work with what we call meta explanation patterns, there's a pretty large meta explanation pattern library that had to be created for the domains we were working in. So the new work we're doing now, and this will also be part of Manish Mehta's PhD thesis, is let's use case-based reasoning to do the meta reasoning as well. We have in the system traces of behaviors. We've got all these avatars. Some are yours, some are other people's. If you're in Second Life, there are lots of shopkeepers and lots of other kinds of standard avatars, and they're greeting their customers and selling and buying or whatever you do in Second Life. Maybe we can look at their traces as cases of what works and what doesn't work. And so here we have 2 execution traces, and what we're going to do is calculate differences and similarities between these traces to identify where things might be wrong. So you might have another failed trace where that behavior didn't trigger, and notice that that's what happened to you. Or you may have a successful trace where the shopkeeper